Hello everyone, welcome to IGC classes. I am Vipin Kumar and this is the demo lecture for heat and mass transfer. So as we all know, GATE 2023 is almost done. Okay, and now we have started the preparation for GATE 2024. And if you have already started the preparation or you are thinking of starting the preparation, then it is a good time. And in this session, what we are going to do, we are going to see that what is the weightage of heat and mass transfer in the GATE exam. Out of the entire syllabus of heat and mass transfer, which topics or which chapters are important. Okay. And we are also going to introduce a brief introduction of the three modes of heat transfer, which is conduction, convection, and radiation. Okay, so it will be a basic introduction. Of course, conduction is a very big topic. It takes around 3 to 4 lectures to cover just the entire conduction, but it is just very basic what we are going to cover, just a basic introduction about the governing laws, about the phenomena, what happens, just the basic things. But more importantly, what we are going to cover is the weightage of heat and mass transfer in the GATE exam and the topics that you must focus if you are planning for, if you are thinking of making a strategy for the GATE preparation. Okay, so before we go ahead, let me introduce myself. Okay, so what we are going to do, a basic introduction of heat transfer. Okay, so my name is Vipin Kumar Yadav. I have done MTech from IIT Kharagpur and I have also done MSc from Politecnico di Milano, Italy. I have around 5+ years of teaching as well as research experience. Now, so before we talk about heat and mass transfer, its weightage, its chapter, let us take a look on the official GATE syllabus. Okay, and now GATE 2024, I know that you're all preparing for GATE 2024 or maybe GATE 2025, but the syllabus of GATE 2024 is not out yet. Where you will get a notification in September or October. Okay, and then only you will get the syllabus, official syllabus of GATE 2024. But if we we can assume that the syllabus, of course, it is not going to change much. 99% of the syllabus will remain same. So it should be, it is a good strategy to start following the syllabus of GATE 2023. Okay, now let's take a close look. What does the GATE 2023 syllabus tells us? So it starts with the modes of heat transfer. This is what we are going to focus on today. What are different modes of heat transfer? Conduction, convection, and radiation. Okay. Now we start with conduction, and this whole portion is one-dimensional heat conduction, resistance concept, and electrical analogy. Okay, it is electrical and thermal analogy, or electrical analogy with the thermal resistances, thermal and electrical analogy, heat transfer through fins, unsteady state heat conduction, and lumped parameter system, and Hassler chart. Everything comes, whatever I have marked here, it comes under the chapter named as conduction. And it is the most important chapter in heat transfer or heat and mass transfer, as you say. Okay, so this chapter is called as conduction. Everything comes, it is the longest chapter. Okay, and it takes the most weightage. It is also most important in terms of the number of questions that are asked from any topic in heat transfer. Okay, then we start with convection, the next chapter or the next big topic. So here we have, let me take some other pen. Okay, so this is convection, thermal boundary layer, dimensionless parameters in free and forced convective heat transfer correlations for flow over flat plate and through pipes, and effect of turbulence. So whatever I have written in red, this whole thing, it comes under the chapter convection. So this comes under convection. Now, one thing is very important to know about convection. It is really complicated. Okay. Now, It is really big, really complicated, and most of the people, most of the students find it hard to understand this topic. The good thing about it, that it is the least, weightage. It carries the least weightage, or least number of questions are asked from convection. Okay, so there's a good thing, there's a bad thing. So what we are going to do, we are only going to cover the portion. Of course we are going to cover everything, but in everything we are going to cover only the points that are important from exam point of view. Because convection is in itself, it is a research topic. Okay, so it's not a good idea to focus on each and everything, because just convection, it is going to take a lot of time to cover. Okay, uh, just one second. Okay, now the next topic, let me take blue color. The next topic is heat exchanger. Okay, let me take green. Okay, next topic is heat exchanger. Okay, so heat exchanger performance, LMTD and NTU methods for the designing of heat exchanger. This green portion is comes under the chapter of heat exchanger. Okay, now moving on. The last topic that our heat and mass transfer subject has is radiation. So now let me take blue color, and this radiative heat transfer, Stephen Boltzmann's law, Wien's displacement law, black and gray surface, view factor, radiative network analysis. This everything that I have marked in blue is comes under the chapter of radiation. So conveniently, I can divide my whole heat and mass transfer. Basically, mass transfer is not there in mechanical syllabus of GATE. Okay, earlier there was a very small portion of mass transfer. So now the subject is just heat transfer, but we have a habit of saying it as heat and mass transfer. Now it is just heat transfer anyway, because the mass transfer portion, the very small portion that used to come in GATE earlier, just even 1% of the total syllabus of heat and mass transfer was mass transfer. Now that is not there in the syllabus, so the subject is now heat transfer only. Okay, so out of the total syllabus of heat transfer, it is, we can conveniently say that it is majorly divided into 4 chapters: conduction, convection, radiation, and heat exchangers. Heat exchangers. Now let us take a look. What is the weightage of the entire syllabus of heat transfer, as well as which topic out of these 4, which topic is more important, or the topics that you should focus more. Okay, now, so now what I have done is, I have taken the weightage of last 6 years. So 2023 data, it has come, but I have not added it yet. I will add it very soon. So if we take the average of last 6 years, we are going to see the weightage of heat and mass transfer from 2017 to 2022. These 6 years, last, the most recent 6 years. Of course, 2023 is more recent, but I have not added it. Okay, so let us talk about these 6 years. Okay, excepting 2023. Now, what is the average weightage? So, this figure is telling you, paper one, how many questions came in paper one, and this one is telling you how many questions came in paper two. There were 2 papers. Okay, similarly, this figure is telling you that 2 questions of 2 marks each came in paper one, and only 1 question of 2 mark came in paper two. Okay, So if you see the average weightage, so I have done it, I have calculated it divided by 2. So if you take the average weightage in 2017, the heat and mass transfer on an average in each paper, it was asked around 3.5 marks. Okay, weightage is in terms of marks. Then in 2018 also it was 3.5, but in 2019 it increased to 6.5, in 2020 4.5, 5.5, and then in 2022 they have asked it for 8 marks. And as much as I know, still I have to confirm it, even in 2003 it consists of around 7 to 8 marks. I again, this figure I have to check one more time. Okay, so again the weightage has increased in 2023, and this must be your motivation to prepare properly for heat transfer. Okay, now see the average weightage in last 6 years, it's around 5.25 marks. Okay, so we can conveniently again say that around 5% of the of total weightage of gate is taken by heat transfer, and 5% is, is not less. And one more thing I'm going to tell you about heat transfer. It's a very easy subject. Okay, and it does not depend on anything, because if you talk about applied thermodynamics, it depends entirely upon how you have done your thermodynamics. If you have not understood thermodynamics properly, basic thermodynamics, then you will never be able to, have a grasp on applied thermodynamics. But heat and mass transfer, it's an independent subject. Okay, and it's an easy subject. If you have a, proper understanding of the concepts, if you have proper understanding of the formulas that we use, and they are very limited formulas except for the convection portion. So you will be able to easily score these 5 marks. Okay, so it's really worth it to prepare heat and mass transfer properly. Now let us see which topics. As I have told you, there are 4 main topics, right? There are these 4 main topics: conduction, convection, radiation, and heat exchanger. So let us take a look which topics or which topic is more important in terms of number of questions that they have asked. Okay, so I have divided into 3-4 main topics. So conduction, convection. Now this portion comes under convection itself, the whole convection. Okay, then radiation, heat exchanger, and this is also a part of conduction. It is also a part of conduction, although we studied separately, but it is also a part of conduction. So you see here the basic conduction and this portion. Even if you talk about the basic conduction portion, the independent conduction portion, in last 6 years, total 10 questions have been asked from basic conduction. But if you also add fins and unsteady state heat conduction, which is also a part of conduction, total, 10 and 5. So conduction, basically, they have asked total 15 questions, which is a very big number if you compare with other topics. Okay, the next important topic is radiation. So I would star mark it. I was also star mark it. Okay, now just one second. Okay, radiation, total 11 questions have been asked in radiation. And again, radiation is a really easy topic, because there are one important topic is view factor here. Okay, most 99% of the time you will get a question from view factor, and it's very easy. It's very, very easy. So radiation, I would say prepare it properly, because if you get a question from radiation, it will be really foolish of you to get that question wrong. It's very easy, and only formula based question they will ask directly. Okay, so the most important 2 topics, if you ask me, in heat transfer, conduction, and radiation. Total 11 questions, and very easy questions. Now heat exchanger also is 8 questions they have asked. Again, it is a very easy topic. Very few formulas are there. Like formulas are there, yes, but these are the same formulas that are repeated again and again and again. If you just have a grasp of the formula and the concept, you will be easily able to score these topics. So heat exchanger and convection. Now you see, that's what I was telling you. This is convection. Now it's a very big topic. So many formulas. Collectively in conduction, heat exchanger, and radiation, we do not have these many formulas that only convection has. So there's so many formulas, so many concepts in convection, but you do not score much here. You see, in basic convection, you have 8 questions. It's not a small number, of course, but it is only basic convection, which is very easy. When you go into complications, then they never ask any question, like 0 questions they have asked here. But you have to study because it is a part of your syllabus. So we have to cover. But in convection, we're going to focus on topics which the topics which you have a possibility or a higher possibility of getting a question from. Okay, those topics, those things we are going to cover now. So I hope that I have given you enough motivation to start your preparation, strategize your preparation, and make or decide heat transfer as an inclusive part of the strategy, because it contains of 5% of the total marks. It's an easy subject, and it's also scoring also. Like if you get a question, it's very it's the thing is that getting the question wrong, it's not basically you always get these questions right if you have a good concept, good grasp on the concept and the formulas. Okay, so let us move on to the topic. The name of the topic is modes of heat transfer. Okay, and it is also the demo lecture. It is also the first lecture which I usually take when I start heat and mass transfer. So it will give you the basic idea of all 3 modes of heat transfer. Okay, just a basic idea what actually is physically is conduction, convection, and radiation. Okay, now, so as I said, I have said this many times, there are total 3 modes of heat transfer around us. Heat transfer can only happen 3 ways. The first one is conduction, the second one is convection, and the third one is radiation. Now, just one second. Okay, so now if we are all okay till now, can you give me a yes or no in the comments so that we can move on? So let's start. So as I have said, 3 modes of conduction, 3 modes of heat transfer: conduction, convection, and radiation. Let us take a look on each and every one of them. Let's get a brief idea about what it means. So let's start with the very first and the most important type of mode of heat transfer. It is called as conduction. Now, what is conduction? Let's break up the definition. First of all, read it completely. It is a mode of heat transfer, of course, that occurs due to temperature difference within the same body or from one body to another that are in physical contact. So what does it mean? What does it mean? You see, let's say you have one body. This is the body, and on one side of it, so this is one side of it, this is the other side of it. Now on one side of it, you have maintained some kind of heat source. For example, you are giving a fire, or you are burning something, or you are heating it just. So some heat source is produced on one side. So that means here on this side we have a temperature T1, and this side we have a temperature T2. And because the heating source is on one side, I can say that T1 is greater than T2. Okay, I don't think there is anything difficult to understand this. Okay, now on one side we have maintained a heat source, and that is the reason that there is a temperature difference between the 2 sides of this solid plate. Let us say on this green side, we have a lower temperature, and at this black side we have a higher temperature. So within this body we have created a temperature difference. Now there will be a heat transfer from this side of the plate to this side, and this is called as conduction. Okay, again let's try to read the definition again. It is a mode of heat transfer that occurs due to temperature difference. So we have maintained the temperature difference, right? And within the same body it is happening. So if you maintain a temperature difference within the same body, the heat transfer that will take place is conduction within the body. Okay, so it happens internally inside the body. Okay, it happens internally inside the body. Now this is the first case. What is the second case? Let us see. You have this body 1. This is body 1, and you have maintained a temperature T1, and you have one more body. Let's say this body 2, and it is a temperature T2. And I am just for my convenience, I am assuming that T1 is greater than T2. T1 is greater than T2. Okay. Now you see there is a distance, there is a space between these two bodies. So there will be a heat transfer between them because of a temperature difference, but that heat transfer will not be conduction until and unless these bodies come in physical contact. So if I bring these bodies in a physical contact, for example, I join them, then because body 1 is at higher temperature, body 2 is at lower temperature, there will be a heat transfer from this body to the other body, and this heat transfer is also called as conduction. Okay, so again let's read the definition. Now when there are two bodies, so conduction happens because of again temperature difference from one body to another body that are in physical contact. So if there are two bodies, then having a physical contact is really, really important. So having a physical contact is really, really important. If physical contact is not there between bodies, then you cannot say that the heat transfer is conduction. That is some other heat transfer. We'll talk about that later. But in order to have a conduction heat transfer between two bodies, if these two bodies have a temperature difference, there must be a physical contact. I hope that it is very clear. Okay. Now conduction can take place in solids, liquids, or gases. Any of them it can take place. Okay. So conduction can take place in all three phases, whether it is a solid, it is a liquid, or it is a gas. So let us take a look on how it happens in all three of them. How it happens in all three of them. Okay. Now let us talk about how the conduction happens in solids. How the conduction happens in solids. Okay. Now there are two phenomena that causes conduction heat transfer in solids. What are two phenomena? Molecular lattice vibration energy transfer and free electron transfer. Okay, because of these two phenomena that happens between solids, conduction heat transfer takes place. So now let's try to understand this. Okay, so you have a solid body, let us say, and there are molecules here, of course. They are bonded with each other. Okay, so let us say they are bonded with each other. Okay, now what happens? Let's say this side, we are giving a heat source Q. Okay, we are having a fire, we are burning some fuel or whatever it is. So basically we are providing some heat, a source of heat transfer, and that is the reason that this surface is at higher temperature T1 than the other surface this side. This side we have a different surface temperature T2. Okay, and because heat transfer is provided on one side, let us say this is first and this is second. Now because the heat transfer or the source of heat transfer is situated on side 1, I can say that T1 is greater than T2. Okay, now what is happening? Let's see. When I have provided this heat source, so this molecule which is very close to the heat source is going to vibrate. They are anyway vibrating, but it is going to vibrate more intensely. So when it is going to vibrate, it is going to provide some energy to the molecule besides it. Okay, so it is providing some energy to this molecule. Now it is also vibrating with higher intensity, and again this one is providing some energy to this molecule. Okay, so now it is started vibrating more. Okay, then this, because of this vibration, what is happening? Energy transfer is taking place. So the molecules that are closer to the heat source, they are vibrating with a higher intensity, so they have more energy, and this energy through vibration is transferred to the nearby molecules. So this is how the energy is getting transferred from molecules at one side to the molecules on the other side. Okay, and this energy that is getting transferred is called as molecular lattice vibrational energy transfer. This is called as molecular lattice vibrational energy transfer. Okay, this is the first case. Now there is one more thing here. In solids, we also have some free electrons. Okay, so there is one free electron here, there is one free electron here, one free electron here, one here, one here. Now what is happening? The electron, this electron which is closer to the heat source is going to go to the higher energy level, and it is going to take a jump. It is going to move around. So it is going to move and provide some energy to this free electron. It is going to jump further and provide energy to this electron. It is again going to move and provide energy to this electron. It is going to move and provide energy to this electron. So electrons or free electrons that are near to the heat source get excited. They start jumping from one location to another and collide with the other electrons, and that is how they transfer energy. Okay, so this is the way free electron energy transfer takes place, and that is how, when you are transferring energy, whether any phenomena takes place, when you are transferring energy and the energy is stored by the other molecule, its temperature is going to increase, and that is how when you go from one side to other, the temperature keeps increasing. Okay, keeps decreasing. Okay, so if there's a heat source here, so what the heat transfer will take place in this direction, q dot conduction will take place in this direction. Okay, now so basically energy of the molecules are going to increase, and it is getting transferred from the side that is near to the heat source to towards the side away from the heat source. Okay, now when we talk about solids, we have metals, right? So when we talk about metals, we know that metals have abundant free electrons. So we have large number of free electrons. Okay, they have abundant amount of free electrons, and that is the reason that metals are good conductor of electricity as well as a good conductor of heat. Because you see, if you have free electrons, and I have told you that free electrons are causing the energy transfer or the heat transfer. So more number of free electrons means more energy transfer, means a better thermal conductor. Okay, so because of the large number of free electrons, it is a good heat conductor, good thermal conductor, and also free electrons causes the flow of electricity as well. So it is a good electrical conductor. Okay. Now you see here, because metals have abundant free electrons, and that is the reason here in metals, free electron energy transfer, out of these two phenomena, free electron energy transfer phenomena dominates. Means out of the total heat transfer, one second, dominates. So if total 100% heat transfer is taking place, 70% will be contributed by this in metals. Okay. Now we have non-metals. Non-metals. Now we all know non-metals have negligible or no free electrons. And that is the reason that non-metals are not a very good electrical conductor also. Okay. Now I can say little or no free electron, no free electrons, or little, let us say, very little, very few. Okay. And that is the reason that most of the heat transfer that is happening because of molecular lattice vibration energy. And therefore, here, molecular lattice vibrational energy transfer phenomena dominates. So it's a very good objective question as well. Okay. In non-metals, which type of heat conduction phenomena dominates? Okay. So if in metals, if they say the free electron energy transfer phenomena is dominating, it's contributing to 70% of the heat transfer. And in non-metals, molecular lattice vibration energy is dominating. Here it is providing around 80 to 90% of the total heat transfer. Very little amount of heat transfer is happens because of free electrons. Okay. Now, what about liquids? What about liquids? So conduction mechanism in liquids. Now liquids, there are two main phenomena that causes the heat transfer. First is collision of molecules, second is diffusion of heat. Now let's try to understand what it means. So what do you have? You have, let us say, a container and you have some liquid in it. Okay, some liquid in it. Now liquid means you will have some molecules in it, of course. Okay, so let us say you have one molecule here, 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 and let us say you have here. Now what I am giving is, I am giving up, heat transfer sources. For example, I have a fireplace here. So I'm transferring some heat here. I'm transferring some heat here. Okay. Now what is going to happen? What is going to happen? So first of all, for example, we have a molecule also here. Now, the molecule that is near to the fireplace, near to this heat source, for example, this molecule, because it is near to the heat source, it is going to consume some energy. It is going to absorb the energy that is being transferred, and it is going to move. So it is going to collide with this molecule. Okay. Or it may collide with this molecule. Okay. So when it is collided, it is going to transfer some energy to the other molecule. So the first reason is when the collision of molecule is taken place. Okay. Now, because these are liquids, and in liquids we have sufficient intermolecular forces. In liquids we have because the molecules are not very far apart, so they have significant intermolecular forces. Now what does intermolecular forces means? It means basically the forces between two molecules. Now because they have certain kind of intermolecular forces, when this molecule is going to jump and collide with this other molecule, it is going to stay together for some time. So these two molecules are staying together for some time, and slowly the diffusion of heat will take place from one molecule to another. So diffusion of heat is a very important phenomena in the heat transfer process. Okay, diffusion of phenomena is very important phenomena in this heat transfer process. Okay, so if someone asks you what is the conduction mechanism in liquids, so there are two mechanisms. First of all, collision of molecules, and then diffusion of heat. So what does diffusion of heat means? It basically, heat is diffused from one molecule to another in physical contact. Okay, because and this physical contact is because of the intermolecular forces. Okay, so one molecule is at higher temperature, other molecule is at lower temperature, and when they collide and stay together for some time, then the heat transfer takes place. Okay, then the heat transfer takes place. So again, what are the conduction mechanism in solids? In solids it is molecular lattice vibrational energy transfer and free electron energy transfer. In liquids it is collision of molecule and diffusion of heat. So there are again two phenomena. Now let us move to gases. When we talk about gases, it is similar, the conduction mechanism in gases is similar as of liquids. So in liquids was collision as well as diffusion. Now the problem here is, what is the problem? That in gases, molecules are far apart from each other. For example, one molecule is here, one molecule is here, one molecule is here. So they are very far apart from each other, and therefore there is no intermolecular forces, no intermolecular forces between molecules, and therefore no diffusion heat transfer. Because if there is no intermolecular forces, they are not going to stay together with each other, and there is no diffusion heat transfer. The only phenomena that happens in gases is because of collision of molecules. Collision of molecules is the only phenomena that is causing the heat transfer. And collision, of course, it is going to depend on the kinetic energy of molecule. Higher the kinetic energy, higher force it is going to put on the other molecule, and more energy can be transferred. Okay, so in gases, heat conduction occurs due to molecular momentum heat transfer when high temperature molecule collide with low temperature molecule. Okay, so the phenomena, so velocity is a function of temperature. Velocity is a function of temperature. Okay, so this is basically molar, this is kinetic theory. Molar mass, and this is Boltzmann constant. And this is temperature. So I can say that velocity square is proportional to temperature. So I can say velocity is proportional to this. Okay. Also, I can say that temperature, if it is dependent on temperature, what does it mean? That it is going to affect our heat transfer as well. So velocity is proportional to heat transfer, and heat transfer we are going to later see that it depends on the thermal conductivity K. So by these two relationships, V and A, I can say V is proportional to, I'm sorry, K is, one second. K is proportional to under root of delta T. Okay. So I can say thermal conductivity is a function of temperature as well. What is thermal conductivity? In little while we are going to see thermal conductivity. Okay. So I hope it is clear. Now, so I hope that the phenomena of conduction mechanism in solids, liquids, and gases is very clear. So again, just to revise, when we talk about conduction mechanism in solids, these two phenomena are responsible for conduction heat transfer in solids. When we talk about in liquids, these two phenomena, collision of molecule and diffusion of heat, these are the two phenomena that are responsible for conduction heat transfer in liquids. And in gases, when we say in gases, only collision of molecules is responsible for heat transfer. I hope it is very clear till now. If there is any doubt, let me know. Then we move ahead. So, okay. Now, let us start with the governing law for conduction heat transfer. There is a governing law for conduction, governing law for convection, and governing law for radiation. So, what is the governing law for conduction? It is called as Fourier's law of conduction. It is the governing law for conduction. There are a few assumptions that we are going to see later on in regular classes, but let us talk about the physicality, the physical significance of this Fourier's law of conduction. Okay. Now, let us try to read the statement and then we are going to understand it. So, Fourier's law states that the rate of heat transfer along a given direction is directly proportional to the area of heat transfer perpendicular to the direction of heat transfer and temperature gradient along that direction. So, what does it mean? Okay, let us say you have a body here. You have a rectangular slab here, let us say. Okay, and this is temperature, this is your x direction. Okay, now let us assume here x is equals to 0, here x is equals to L. Okay, now I have a heat source here. I have a heat source here. Okay, and I am only assuming that it is heat transfer is taking place in one direction, Qx. Okay, only in one direction. Now, because I have a heat source here, this side, let us say this is side 1, this is a side 2. So this side will be at higher temperature T1. Okay, and the other side, of course, it will be at lower temperature T2. Okay, now, and if there is again in the beginning, remember the definition of conduction. So whenever in a single body, if you have temperature difference, the heat transfer, the internal heat transfer that will take place is conduction heat transfer. So now again we have a temperature difference internally inside the body, so heat transfer will be conduction heat transfer. Okay, now let us try to understand what it is saying. Okay, and we know that T1 is greater than T2. Okay, so it is saying that the Fourier law states the rate of heat transfer along a given direction. What does it mean? Rate of heat transfer along a given direction. Okay, when I say rate of heat transfer, I mean Q dot. Okay, joules per second in a given direction. So given direction, let us say x direction. I am assuming. Why I am assuming only x direction? I have neglected the heat transfer in y and z direction. Okay, that is the reason. That we will see in assumptions later on in the regular classes. Okay. Anyway, we only take unidirectional. Okay, one directional heat transfer. Okay, and it is directly proportional to the area of heat transfer perpendicular to the direction of heat transfer. What area? Perpendicular to the direction of heat transfer. So if this is the direction of heat transfer, if this is the direction of heat transfer, what is the perpendicular area? This area is the perpendicular area, right? This area is the perpendicular area. Okay, this area, the black area. Or if you ask, this area as well. Okay, this area is perpendicular to the heat transfer. Okay, now what is the area? Let us say this is my width, this is my height, so this is the area perpendicular to the heat transfer area. So ये है perpendicular area. Now what is my area? It is equal to width into height. Okay, and it is also in it is also proportional to temperature gradient along that direction. Temperature gradient. So what do you mean by temperature gradient? Temperature gradient is dt in the particular direction. So what is the direction? X direction. So if you ask what is dt by dx, it is this. If I am going from T1 to T2, 1 second. Okay. If I am going from T1 to T2, this is my dt, right? This is my dt and this is my dx. So it is also giving me the slope of the temperature gradient line. Okay. So dt by dx. Okay. Now you see here, what can I write here? As I am going in x direction, you see, as I am moving in positive x direction, this is positive x direction, temperature is reducing, temperature is coming down. Okay. So as I am going in positive x direction, my temperature is reducing. You can also write it like this, ki T2 minus T1 upon x2 minus x1. So x2 minus x1 will be a positive term, but because T1 is greater than T2, that means T2 is smaller, the numerator will be negative. So whatever you get, you will get this a negative term. Now to make this positive, I will add a negative sign here. So this term will always be positive. This term will always be positive. Okay. So by joining these two, I can write Q dot X is proportional to perpendicular area into dt by dx. dt by dx. Okay. Now, moving forward, let me just simplify it. So what have I written? Q dot X dot conduction is proportional to perpendicular area dt by dx. Okay. And let me put minus sign here. Okay. Now, when I have to remove this proportionality sign, what will I write here? Q dot X of conduction is equals to, I'll take a proportionality constant. This minus I'll bring outside. Okay. K is the proportionality constant, a perpendicular area dt by dx. Okay. Now K, we are going to see in a little while, it is called as thermal conductivity. Thermal conductivity, and the unit is watt per meter Kelvin. Okay. So let me check the units of this. This is watt per meter Kelvin. This is meter square, and temperature. Temperature will be in Kelvin. Dx will be in meter. So meter will cancel this. Kelvin will cancel this, and you will get this into watts or joule per second. Joule per second. Okay. So if someone asks why have you added this minus sign here, so minus sign is added. Negative sign is added to satisfy second law of thermodynamics. What is the second law of thermodynamics? That heat transfer will always happen. Heat transfer will always happen from high temperature to low temperature. So simply put, what can I say? This side x is equals to 0, and you are starting the heat transfer here. So T1 is here. So of course, when you are going in your x is going to increase and temperature is going to decrease because temperature is higher here. Okay. So as you are going in positive x direction, temperature is going to decrease because heat transfer takes place from high to low temperature. Okay. So this is your Fourier's law of conduction. What is that? It's very important. Okay. Minus k perpendicular area dt by dx, and it is given in watts. Okay. Very important. Now Let's talk about the concept of thermal conductivity. Concept of thermal conductivity. So basically, our Fourier's law is the defining equation. Q dot X conduction minus Ka dt by dx. So this is the defining equation. It is our Fourier's law, right? This is my Fourier law. And it is also the defining equation for thermal conductivity. Defining equation for thermal conductivity. How defining equation? So let me write K is equals to Q dot X conduction into dx upon area into dt. I'm neglecting the negative sign for some time. Now what does it mean? You see, you have a body, with a unit thickness. Dx is equals to 1. Unit thickness means 1 meter, let us say I am assuming. And area also I am assuming per meter square, yani ki 1 meter square. And temperature difference I am assuming 1 degree Celsius or 1 degree Kelvin. So what do we have? If I put the values here, I will have Q dot conduction 1 into 1. So K is equals to Qx conduction. Now what does it mean? It means that thermal conductivity is defined as the rate of heat transfer. You see, thermal conductivity is defined as the rate of heat transfer through the unit thickness. Unit thickness means the thickness. You see, I have drawn that earlier, this part. So this is 1 meter only, unit thickness, dx, x1, x2. Unit thickness I am assuming of the material, and per unit area. Per unit area means I am assuming my width is equals to 1 meter and my height is also is equals to 1 meter. And per unit temperature difference, that means the temperature difference between T1 and T2 is 1 degree Celsius or 1 degree Kelvin. dt is equals to 1 degree Celsius or 1 degree Kelvin. Okay, so it is defined, K, thermal conductivity is defined as the rate of heat transfer when we take a unit thickness of the material and per unit area per unit temperature difference. So I can simply say that thermal conductivity or heat transfer is a function of thermal conductivity. Higher the thermal conductivity, higher the rate of heat transfer. Okay, so it basically tells the ability of the material to conduct heat. Its unit is watt per meter Kelvin, and it is a property of material. It is a property of material. Okay, now let us see some conventional values of thermal conductivity. Conventional values of thermal conductivity. So you see here that in metals, of course, the unit is watt per meter Kelvin. Watt per meter Kelvin. Okay. So you see in metals, it is in the range of 10 to 10 to the power 2. Okay, it is mostly in the range of hundreds. Okay, so aluminium is 200, copper is 385, silver is 410, iron is 80, steel is 15 to 35. So basically, metals have a very high thermal conductivity. Metals have a good thermal conductivity, let's say. And that is the reason, because thermal conductivity is high in metals, so heat transfer through conduction in metals is really high compared to non-metals and liquids and gases. Now, when I talk about non-metals, so in diamond is an exception. Diamond has a very high thermal conductivity, 2300. No metal or any material in the world can match this thermal conductivity. Okay, and it is an exception. The reason we are going to discuss in our classes as well later on. But in short, I am going to tell you because it has a perfect crystalline structure. You see, metal, solids can conduct heat by two ways. What is the first way? The first way is molecular lattice vibrational energy. Second is free electron transfer. So it has so perfectly arranged crystal structure that the molecular lattice vibrational energy transfer takes place 100 times faster than free electron transfer. Okay, so that is why the thermal conductivity is really high. Then glass, you see it's very low. Glass wool is really, in fact, glass wool sometimes is used as insulation to heat transfer. Okay, because very low heat transfer, thermal conductivity, so very low heat transfer. Okay, then liquids, mercury has a good thermal conductivity. Water is again low. Hydrogen very low. Gas is basically very low. So if I need to conclude this, I can say thermal conductivity of metals in general, I am telling you, okay, in metals is greater than thermal conductivity of non-metals. Then it is thermal conductivity of liquids, and it is greater than thermal conductivity of gases. Of course, here diamond is an exception. Again, we are going to see that in detail in our regular classes. Diamond is an exception. Okay, I hope it is clear. Okay, now let us see this question. Let us arrange. It is also a gate question. In descending order, we have to arrange. Descending, yani ki the highest thermal conductivity will come first. So the thermal conductivity of pure iron, liquid water, saturated water vapor, and pure aluminium, I have to arrange them in decreasing order. Decreasing order. So if you remember, I have in general I have told you that K of metals is K greater than K of non-metal, is greater than K of liquids, is greater than K of gases. So of course liquid will come here, right? So B will come here. Then saturated water vapor is a gas. So water vapor will come here, C. Now iron is also a metal and aluminium is also a metal. So I need to compare. Now if you remember, what is the thermal conductivity of iron? You see, iron has 80, aluminium is 200. Iron is 80, aluminium is 200. That means iron is 80 watt per meter Kelvin and aluminium is 200. So which one is the highest? Aluminium, of course. So D will come here and A will come here. And this is your arrangement, correct arrangement in the decreasing order. So D, A, B, C is the right answer. I hope it is clear. Okay. Now let us see one more question. Fourier's law is the governing law for. Okay. It's a very basic question because I have covered just now. But if I ask you the same question after 3-4 lectures in my class, because I have seen this, then usually people tend to forget the name of the governing law for conduction. Okay, they do not remember. So it's important to remember that the Fourier's law or the governing law for conduction is Fourier's law. So Fourier's law is the governing law for conduction. Okay, so let us move on. So the basic introduction of conduction is done. Now let us move to convection. Let us move to convection. Now what is convection? Convection, it is a mode of heat transfer that occurs between a solid body and the surrounding fluid due to temperature difference associated with macroscopic bulk motion of the fluid transporting thermal energy. Now, of course, I have read out a very long sentence, but we are going to break this and see. Okay. Convection. We are talking about convection. So it is a mode of heat transfer. We all know conduction, convection, and radiation. They are modes of heat transfer. Okay. That occurs between a solid body and a surrounding fluid. So what does it mean? Let us make a solid body here. So we have a solid plate here like this. And let us say it has a surface temperature Ts. Okay. And then we have some, fluid that is flowing here. For example, air is flowing here or water is flowing here. And it is at T infinite. And I can say, just for the assumption, that surface is basically the temperature of this surface. Okay. This surface is at some temperature Ts. This surface, upper surface. Below surface can be at any temperature. Let's forget that. But this upper surface is at Ts. So let us say that Ts is greater than T infinite. Now what is going to happen? You see, when this fluid will come and it is going to, fall on this surface. It is going to absorb some heat. Okay, it is going to absorb some heat, and because it is going to absorb some heat, its temperature is going to increase and its density is going to decrease. So it is going to come here, absorb heat and move upward. Similarly, this fluid will come, absorb heat and move upward. Similarly, this fluid will come, absorb heat and move forward. So what does it mean? It means that this heat transfer, first of all, it is happening between a solid body and a surrounding fluid. Now, I hope you all know fluid can be, when I say fluid, it can be liquid or gas, any one of them. Okay, it means anything. Okay, so it is happening between a solid body and surrounding fluid, and there is a temperature difference between these two. Okay, so there is a temperature difference that is causing this, and associated with macroscopic bulk motion. You see some motion is happening here. Fluid is coming, taking heat and moving away. Fluid is coming, taking heat and moving away. So some kind of motion is continuously taking place. If the motion is not there, that means it is not convection. It is not convection. It will be something else. What will it be? We will see later. But in order for convection to take place, what do we have? First of all, there should be a solid body, there should be a surrounding fluid. Then there must be a temperature difference, second condition. Third is a macroscopic bulk motion, yani fluid motion must be there. So first of all, it will happen at the interface. You see, the fluid is not entering inside the body, it is only happening at the surface, at the boundary. So it is called as interface or boundary or surface, whatever you want to call it. And that is why it is also called as surface phenomena. Okay, and then temperature difference is also required, and fluid motion is required. Okay, now these three conditions must be satisfied to call it as convection. Okay, now what is the difference between conduction and convection? So you see, conduction, when I was talking about conduction, I was telling you about either it is going to happen inside the body, okay, or between two bodies, but it will always happen inside the body. So therefore, it is a internal phenomena. It is a internal phenomenon, and it would require a physical contact. It will require a physical contact between two bodies if there are two bodies. Okay. Now, when I talk about convection, it will always occur at the surface. So it is a surface phenomena or boundary phenomena or interface phenomena. Now, it can happen between, here I have told you, it is happening between a solid and a fluid. But it can also happen at the interface. So you see, we have a surface, but surface between what? It could be a solid and a fluid, or it could be a fluid as well. It will be a fluid and fluid. For example, solid and fluid I have just shown you, but what about fluid? For example, there is water here, a heated water. Okay, water is at, let us say, 100 degrees Celsius, and let us say some air is flowing here, and as soon as it touches the surface, it is going to take up some heat and move forward. Similarly, air is coming, touching the surface, taking some heat and moving away. Let us say this air is at 30 degrees Celsius. Okay, so as soon as it is coming, it is taking heat and moving away. It is coming, taking heat and moving away. So all the the conditions are satisfied. Why? The first condition is it is happening at interface, right? First condition. Second condition is what? There is a temperature difference. So water is at 100 degree and air is at 30 degree. So temperature difference condition is also satisfied. And what is the third condition? What is the third condition? Third condition is that fluid motion. So fluid motion is also taking place. Air is coming and taking heat and moving away. So fluid motion is also satisfied. So all three conditions are satisfied, and we can call this as convection, we can say. Okay, so the most important criteria here is fluid motion. And that is the reason that based on the convection, what is important? Fluid motion is important. Fluid motion is important. Now, based on the forces, based on the forces causing fluid motion, what is causing that fluid motion? We can divide our convection as free convection and forced convection and forced convection. Now, what does it mean? Free convection. Free convection means that there is no external force that is causing the fluid motion. No external force is used. No external force. The fluid is moving due to only buoyancy forces or natural forces. You see, when fluid gets heated, its density decreases, it will move up. When fluid gets colder, its density increases and it moves down. So density changes or buoyancy forces. Okay. So buoyancy forces are causing, which are natural forces, right? Buoyancy forces are causing the fluid motion. But when we talk about force convection, now here the motion, fluid motion is caused due to some external forces, due to external forces. What external forces? External forces. For example, a fan, a blower, a pump, whatever it is. Okay. So if you want to see here, let us see. Let us see what does it mean. When I talk about free convection, okay. So let us say you have a surface here. Okay. And let us say you have a hot ball, steel ball here, hot ball here, right? Now some air is coming at, let us say this is at higher temperature T surface, and this is at lower temperature because Ts is greater than T infinite. Now the air is coming, it is coming in contact at the surface and moving away, moving upward. This air is coming, taking some heat, becomes less denser and moving away. Okay, so again some air is coming, taking heat and moving away. Now what is causing this motion? You see, when the air is coming, so air is getting heated, air is getting hot. That means temperature of air is increasing. When temperature of air is increasing, what will happen? Density of air will decrease. That means it will become lighter, and if it will become lighter, it will move upward, and that is how it is moving because of only density difference. Okay, now let us take one more example, forced convection. What is the forced convection? So again, same example, you have a surface here, you have a hot ball here at some temperature Ts. Okay, now you have installed here a fan. You have installed a fan or a blower or something. Installed a fan. Now fan is running. Now whatever air is coming here, let me draw this with a different color. Whatever air is coming here, now air will not move upward because this fan is pushing the air in forward direction. So air will come, take heat, and move in the forward direction. Air will come, take heat, and move in the forward direction. Now in the back side of it, of course, lekin it will move in the forward direction. It is not going in the above, upward direction, because in upward it was going because of density difference. Now fan is pushing the air forward in the forward direction, so it is giving much force. The force applied by the fan is greater than the buoyancy forces or the natural forces, and that is why the fluid motion is guided by the fan or the force that is applied by the fan. So this is called as forced convection. This is called as forced convection. So if you remember, we had a governing law for convection. Similarly, we have a governing law for convection. What is the governing law for convection? It is defined as Newton's law of cooling. For convection, it is defined as Newton's law of cooling. Let us see what it is saying. Newton's law of cooling states that the rate of heat transfer by convection is directly proportional to. So it is saying rate of heat transfer by convection is directly proportional to temperature difference between the body and its surrounding. So what is the temperature difference between the body and the surrounding? You see, let us say this is the body. It is at surface temperature Ts and surrounding temperature is T infinity. So can I say temperature difference is Ts minus T infinite? I can say this, right? Then it is also proportional to area of heat transfer. What is the area of heat transfer? Tell me. Area of heat transfer. The area exposed to the fluid. So this whole area is exposed to fluid. Okay, so this is my area of heat transfer, length into width, right? So this is my area of heat transfer. So area of heat transfer. So by combining these above equations, I can write that is proportional to area of heat transfer into Ts minus T infinity, right? So what can I do? I can replace the proportionality sign with a constant H, area of heat transfer, Ts minus T infinity. Okay. Now what is H? H is called as convective heat transfer coefficient. And its unit is watt per meter square Kelvin. So many things we are going to discuss about convective heat transfer coefficient when we study convection in detail. So many things, all the convection studies based on this convective heat transfer. Because why? Because it is not a property, it is not a property of material. Property, it is defined experimentally, property of material. Okay? It is defined experimentally. Defined experimentally. Okay, so if you ask me the units, it is watt per meter square Kelvin. This is meter square, this is Kelvin. So meter square, Kelvin, Kelvin. The units that are remained is basically watts. So very important to understand, this is your Newton's law of cooling. Very frequently we are going to use this. Okay, so I hope it is very clear. So let us see a few ranges. Okay, this is done anyway. Let us see some ranges of heat transfer coefficient. Okay, now as I told you that heat transfer coefficient, so basically heat transfer coefficient is not a property of material. It depends on a lot of parameters. For example, it is a function of velocity of the fluid. It depends on the characteristic dimension. It depends on the density of fluid, viscosity of fluid, specific heat of fluid, thermal conductivity of fluid. So it is a function of flow parameters as well as fluid properties. Okay, so what we have seen here is that free convection, of course free convection is have lower velocity. Okay, so free convection will have lower velocity. So if velocity is less, h will also be less. Okay, so free convection in gases is basically 3 to 25 range is there for heat transfer coefficient. Okay, convective. If we use forced convection, then we have 25 to 400. Now if we have free convection but we are dealing with liquids, then this is the range. That means it is increasing. Now with water itself, if we talk about forced convection, then 600 to 400. Then condensation is 3000 to 2500 and boiling is the highest one. Okay, now by comparing these two, can I say that H of free convection is less than H of forced convection? So this is one conclusion I can carry out, right? Now comparing these four, can I say H of gases is less than H of water, H of liquid, right? Q gases, you see these gases, these ranges are less than in liquid, okay, than in liquid, okay. So this is also one conclusion I can draw. What else? What else? And I can also draw this heat transfer in boiling is highest, then heat transfer in conduction, then heat transfer in liquid with forced convection. I am not asking you to remember these, okay, but at least this conclusion you must know. Liquid free, it is greater than gas forced, and is greater than H of gas of free. So at least this conclusion, these few conclusions, 1, 2, and 3. First conclusion, second conclusion, and third conclusion, you must understand. You must understand. Okay. So what is this question saying? Convective heat transfer coefficient for forced convection in liquids. Forced convection in liquids is in the range of, what is the range of forced convection in liquid? So this is the range, 1000 to 400. 1000 to 400 is the range. Okay. So till now we have seen a brief introduction of conduction. We have seen a brief introduction of course there is a lot more than this, but just to introduce this we have done conduction and convection. Now let us move to the last mode of heat transfer, which is radiation. So what does it say? Now let us see. Let us consider a hot body. A hot object we have taken. Okay, this is the ball. This is the ball. Hot ball, and it is suspended in an evacuated chamber. Suspended in an evacuated chamber. That means no surrounding fluid, having walls at room temperature. So this is at room temperature, okay, T infinite, and of course T of ball is greater than T infinite, okay. Now let's tell me one thing. Do we have so what we can see, there is no physical contact. The ball is not touching this ball is not touching the surface, wall surface anyway, okay. So there is no physical contact. So because there is no physical contact, I can say there is no conduction, right? Because for conduction, we require physical contact. Now also the room is evacuated. That means there is no surrounding fluid, right? There is no surrounding fluid. So if there is no surrounding fluid, I can conveniently say there is no convection, because for convection, I require surrounding fluid. But still, what is going to happen, you see? But still, after some time, so with time, the ball will cool down. The ball will cool down eventually to room temperature. After 2 hours, if you see, or 3 hours, if you see, the ball will be at room temperature. Let us say T infinite. So what is happening? Okay. So when it reaches T infinite, thermal equilibrium is achieved. Thermal equilibrium is achieved. I hope you all know what is thermal equilibrium. That means equality of temperature. In general sense, we can say. Otherwise, it has some more meaning as well. But in general sense, I can say this. Okay. Thermal equilibrium is achieved. Now you see here, there is no conduction happening, no convection happening. Then why this cooling down of ball has taken place? How the ball has come to the room temperature? So the phenomena that is working here is radiation. So the phenomena that is responsible here is phenomena responsible for this type of heat transfer. This heat transfer is radiation. So can I say radiation? It does not require any physical contact. It requires no physical contact. Also, it requires no surrounding fluid or material medium for its propagation. Material medium. Then how does it happen? How does it happen? So you see, in conduction and convection, it requires material medium for heat transfer, but in radiation, it does not require any material medium for heat transfer. So how does it happen? It happens because of electromagnetic waves. Electromagnetic waves. Okay, what are electromagnetic waves? By ultraviolet rays, infrared rays. Okay, all these are radio waves, microwave, X-rays, gamma rays. These are all ultraviolet. Okay, so for most of the practical applications, all the modes of heat transfer work simultaneously: conduction, convection, and radiation. But which phenomena is dominating? That actually depends on the the operating conditions, how you are operating, at what temperature you are operating all on all these parameters. It depends which phenomena: conduction is dominating, convection is dominating, or radiation is dominating. Okay, so now I have told you there are so many electromagnetic waves. Here we have thermal waves as well, thermal radiation as well. Now the phenomena that is responsible for radiation heat transfer is thermal radiation. Thermal radiation. So thermal radiation is electromagnetic radiation emitted by a body as a result of its temperature. If a body is at temperature, at any temperature, so you see, a body is at any temperature which is greater than 0 Kelvin. Greater than 0 Kelvin, it is going to emit some thermal radiation. So, and I hope that you all know that it is impossible to achieve 0 Kelvin. So whatever bodies are there around us, it is 101%. It will be above the temperature of 0 Kelvin. It will be above 0 Kelvin, and that is the reason that all the bodies are going to radiate the radiate the thermal radiation. Okay, they will be emitting thermal radiation, and they will be taking part in the radiation heat transfer. Now, how intensively they are radiating or they are emitting thermal radiation, it depends on their temperature. For example, if this body T1 is there, if this body A is there, it is at temperature T1 100 Kelvin, and this body 2, let us say it is at 50 Kelvin. So because it is at higher temperature, it is going to radiate an thermal radiation and more thermal radiation. But this body B is at 50 Kelvin. That means it is at lower temperature. So it is going to emit radiation, but lower radiations. Okay. Lower radiations only. Okay. So the higher the temperature, the higher will be the thermal radiations emitted by the body. So all body at all temperatures emit thermal radiations except at 0 Kelvin. Two bodies, one at higher temperature and one at lower temperature, both bodies will radiate and receive heat simultaneously. Body A will radiate more energy than it will receive. Okay. So before we move forward, we will see the governing law. We have to understand what is a black body also, because black body works as the ideal body for radiation heat transfer. Okay. So we all know black body is a perfect emitter and a absorber of radiation. What does it mean? It emits all radiation that falls on it. It emits all the radiations that falls on it, and it also absorbs all the radiation that falls on it. It absorbs all the radiations. Okay, so absorbs all incident radiation regardless of wavelength and direction. Whatever the wavelength, whatever the direction, it is going to absorb all the radiation that are falling on it. Okay, and also at a specified temperature and wavelength, there is no surface that can emit more energy, because it is a perfect emitter. Therefore, it can emit the maximum energy than any other body. A black body can emit maximum radiation than any other body. So black body emits radiation energy uniformly in all directions. You see, if it is a black body, it is going to radiate energy uniformly in all directions, uniformly. So you see, this is a uniform distribution of radiations. Okay, but this is not uniform. You see, this is not uniform. Okay, and these types of body, we can say that here emission, that radiation that are emitted, they are not a function of direction. They are not a function of direction. They are not a function of direction. Okay, so let us come to the last topic, which is called as the governing law for radiation. So the Stephen Boltzmann's law is the governing, although there are other laws as well, governing law of radiation. Although there are other laws as well, Planck's law, Wien's displacement law, but Stephen Boltzmann's law is the governing law for radiation. What does it says? It says that the law states that the radiation emitted, energy emitted from the surface of a black body per unit area per unit time. So radiation energy emitted, radiation energy is shown by EB. Okay, now it is per unit area per unit time is directly proportional to fourth power of the absolute temperature of the black body. Okay, so what does it mean? If you have a body here, and let me assume it is a black body, it is a black body. Okay, so let me assume it is a black body. Now the radiations that it is emitting, so this is the area, and the radiations that it is emitting is basically depend on the absolute temperature of this black body, temperature of this black body. And very important, it is the absolute temperature. This must always be given in Kelvin. It must be given in Kelvin, must be given in Kelvin. Okay, so if I remove this proportionality sign, I can write EB is equals to sigma T to the power 4. What is this sigma? Sigma is Stephen Boltzmann's constant. Stephen Boltzmann's constant, and its unit is watt per meter square, Kelvin to the power 4. Okay. Now, what is the unit of this? Energy per unit area. So, what is the energy? What is the unit of energy? What is the unit of energy? Joule. Okay. So, energy emitted from the surface per unit area means meter square, and per unit time means second. So this is the unit, or I can write watt per meter square as well. If I need to calculate heat transfer by radiation, I can multiply this EB by area. So it will be, what is this? Watt per meter square. It is meter square. So it is equals to watts. Okay. I hope it is clear. Okay. So this is the end of this demo class. Now let's summarize what we have done till now. So we started with the modes of heat transfer, right? Modes of heat transfer. What are different modes of heat transfer? First is conduction. So what we have seen what is the definition of conduction, and we have seen the mechanism of conduction heat transfer in solids, liquids, and gases, right? So what do we have in solid? Molecular lattice vibrational energy transfer and free electron transfer. Okay, what is in liquids? Collision of molecules and diffusion of heat. What about in gases? In gases, it's just collision of molecules. Okay. Then furthermore, we have talked about the governing law for conduction. Governing law. What is governing law? Fourier's law of conduction. This is what we have talked about in conduction, right? And we also talked about the concept of thermal conductivity, isn't it? Thermal conductivity concept. What is the unit? Watt per meter Kelvin. Then we came to convection. Convection. Okay. So we started with definition. We started with types of convection: free and forced convection. We also saw the governing law. What is the governing law? Newton's law of cooling. Newton's law of cooling, right? And we also briefly saw about convective heat transfer coefficient. Although, of course, it is not enough, but just introduction part of it, convective heat transfer coefficient. Because in convection, we only talk about this convective, how to calculate convective heat transfer coefficient. This is the only problem that we have to solve in convection. Then finally, we came to radiation. We came to radiation. Again, what did we talk about? Definition. Black body we have seen. And the governing law, which is Stephen Boltzmann law. Okay. So this is what we have done in this class. And I hope that you have enjoyed this session. Okay. So now I think this is the right time to start the preparation for GATE 2023. Okay, and if you want us to guide you, there are few contact numbers that are given. You can contact this. Okay, but anyway, start your preparation, because this is the right time. Even if you want to do it yourself, you want to join some institute or whatever you want to do, but this is the right time. Start your preparation, plan your strategy, whatever you want to do, and just what do you say, uh, come up with a plan what you want to do. Okay, come up with a plan, what should be the strategy, and have an objective of what rank you want to get, what kind of marks you want to achieve, and start your preparation strategy accordingly. Okay, so I hope it's done, and very soon we are going to meet again in regular classes. Okay, so goodbye till then. Bye bye. Thank you so much.